Grateful to organizers for inviting me for this Matfest, honoring the 40 years of beautiful Sasha Borichev career, and some age, of course, also. And I also very happy to be with Sasha from the very beginning, when he was the PhD student in Steklov Institute in St. Petersburg. In the list of my students is somewhere between Nikolai Makarov and Evgeny Abakumov, just in the middle of this interval. And so I think that there will be a lot of occasions to speak here about Sasha's mathematical result. I will not do it immediately now, because I have my own subject which I like to present here. But what it seems to me important that we look not only ahead in the mathematics which is actual now and for future results and so on, open problems, but also to the back, from where we come. I mean, Sasha and me also, and many others of you. So I regarded the mathematics genealogy project to see our path to the previous times. And so the result is here. So starting from Sasha, we go to the previous centuries. Our common teacher, I can say, was Victor Haven, who founded St. Petersburg Analysis Seminar after the Second World War, and who was a student of Kantorovich and Vladimir Smirnov, a very known person in our kind of mathematical analysis. And both Smirnov and Kantorovich came from Vladimir Steklov, whose name is for the institute here. It was not so great mathematician as other in this list, but it was the first one. He take part of the Bolshevik power in Russia. And Steklov come from Lyapunov and Chebyshev, so I can say also St. Petersburg and Kazan mathematical school. And Chebyshev come from not so known Nikolai Brashman, who was the, in fact, Russified Austrian mathematician, who was a student of Litrow and Ostrogradsky. And Ostrogradsky, in some miraculous way, was a student of Poisson and Cauchy here in France, in Paris and in Berlin. And Cauchy had no any PhD advisor, and Poisson came from Euler, and Euler from Bernoulli family, from Basel School, and Basel School to the medieval Germany, and then the traces was dissipated. There was many changes and so on. From my observation, it is my some mathematical history discovery, that in Russian-based mathematics of 2 or 3 last centuries, there is 2 connected components in the original trees. One came by Chebyshev and all this way to the French school and finally to Euler. And another one came by Luzin and Yegorov and then Weierstrass, and directly to Germany. So it's maybe I'm mistaken, because this equations are very delicate, but it seems that exactly two connected components. So, but now I will come to my subject. My subject is the behavior of the orthonormal basis, Riesz basis, and frames, and just Bessel sequences in L2 spaces with respect to a measure. It is so we will place ourselves on the metric measure space, omega, compact, and we'll consider the embedding of the Lipschitz functions to the L2 mu and the Sobolev kind of spaces which I will define and whose definition is just another history, another story. So I will consider the approximation numbers of this compact embedding, because it's compact, it's very simple, of this. So approximation number, so the best possible approximation by operator of the finite rank, n given. And then so the summability property of these approximation numbers, so the Schatten-Neumann classes of this embedding. And the answers was depend on the dimension, which is not surprising, but however, the difference from the usual Euclidean case is that here we have several dimensions, several different. So the geometric dimension of the compact, which was supposed to be the homogeneous space, and so the two dimensions of the measure, the upper dimension coming from the halving condition on the measure, and the lower coming from the doubling condition on the measure. And so I will define all this object, but first two words about the motivations. The motivations are here, just the curiosity, of course, and on the other hand, the Sobolev type spaces on the more or less arbitrary compacts like trees and so on. So it is of interest for many applications, and there is no, it is not so clear how to define it correctly. There is several definitions, they are not always equivalent. I will discuss it a little bit later. But for me, the principle, unfortunately, the pointer does not work, so I cannot point it. And no, there is no. Yes, I'm sorry, it is. For me, the principal motivation is here. It is the application to so-called positivity phenomena for representing basis. For the importance of this problem and just its existence, this is Dima Yakubovich who attracted my attention some years ago, 5 maybe, and this is the following. So we consider the representing system in the space of functions. So I mean that we have just the series, convergent in some sense, weak or strong in various things. Phi of k is some functionals, linear or not. There is no uniqueness and so on. The representing system just the possibility to, to represent any function of the space in this way. And for many applications in computing mathematics for algorithm and so on, the positivity property is very important in different senses. The positivity of the functions uk in some subset of positive measure, or the positivity of coefficients. Anyway, it is a large literature about this, and the first who attracted the attention to the importance of this property was Vladimir Glaser of Odessa, who wrote several books about this application, especially in neurosciences. And there is a visible constraints. The basis and representing system cannot be non-negative. Say, the orthogonal polynomials need to have some zeros, and it was observed even in 1916 by Kellogg, the founder of potential theory, that this is a very general, not only polynomial, but just more or less arbitrary orthonormal system, has many positive and negative values, of course. And in 1948, Vladimir Kozlov in Steklov Institute just proved that the amount of the positive and negative values of an orthonormal basis are the same, and the both series diverges here, so the L2 masses of negative and positive values of an orthonormal basis in L2 with respect to Lebesgue measure are infinite and the same. And then, so it was generalized already in the 21st century, just recently, I can say, by Powell and Spies, proves that the same is true for any unconditional basis in LP for a continuous measure mu, of course. If mu is discrete, it's not the case, obviously. And then Sasha Wahlberg and me proved that the same is true in general for arbitrary reflexive Banach space in between of L1 and L infinity with respect always to a continuous measure mu. And the more or less that the amount of positive and negative values of an unconditional basis, normalized unconditional basis, is always infinite in this sense if we consider in LP. So for small p, it is the L2 norm of these values is infinite, and for p larger than 2, so it is the conjugate exponent here. And these constraints are optimal. All changes, if we consider the non-unconditional, but just basis in the Schauder sense. In this sense, so the Johnson-Schachtman and this company with Powell also proved that there exists a non-negative Schauder basis in L1 with respect to any continuous measure and in L2. Astonishingly, this fact is unknown for P different from 1 and 2, to my knowledge. Maybe there exists something. So anyway, for me, the reasons of this possibility to measure the amount of positive and negative values is just in the definition. If you want that your representing system is unconditional basis, so converges with any permutations and so on, it should oscillate rather fast. But if it oscillates too fast, it's not complete. And this is in between of these two possibilities. We will what is the frequency? The frequency, there is no chalk up.
On the table in the middle.
Oh yeah. Oh yes, yeah, thank you. Yeah. So in the, of course, if you have, so we will measure it by the work needed to transport the positive values to the negative one, with the mean value of the function equal to 0. So this work is quite small, but if we consider twice frequent system, so the distances between the plus value and minus value should be lesser, and so the work needed with the same quantity of the masses of positive and negative values, and so the work to transport the positive value to negative will be less. And so the natural way to measure the frequency of an arbitrary function on arbitrary compact where there is no intervals, it is the work needed to transport the positive value to negative. It is very known construction, which is called optimal transport norm of Kantarovich-Rubinstein. And so I will use this. This is the reminder of the definition. We consider the transportation plane psi. Psi is just a non-negative measure on the product omega on omega, satisfying this conservative condition, so the masses not disappeared and not appeared. It is the same as before. Nu and lambda are two non-negative measures on omega, and so the product of the distance on the work, this psi has the meaning of how many masses you need to transport from sigma to sigma prime. And so this integral represents the work following the plan of transportation psi, and we take the infimum with respect to all such plans satisfying this condition. This is the Kantarovich definition, which counted for Nobel Prize in economics. And so it does not work. Yes, it stopped. No. I'm sorry. Okay. And the principal property of Kantarovich-Rubinstein norm, that first, this is the norm on the set of all real valued measures with the zero mean as here. And it is the normed space, not Banach, but normed. And the principal property is that this is the dual norm of the Lipschitz space, the space of Lipschitz functions with the Lipschitz norm as a supremum of the ratio divided difference by the distance. And this is Kantarovich-Rubinstein principal theorem. And so I will use this definition. I will fix the measure mu, continuous measure on omega, so without point masses, and I will consider the corresponding L1 space, and for a function, real valued function with the zero mean, I will consider this Kantarovich-Rubinstein norm for measuring the work needed to transport positive values of u in the negative values of u. So it's this example here, so it illustrates what I this picture. So if you have say the sign u of x, and if you have and continue is periodically to the real axis, and if you have the multiple argument function, so the function like this, so you will have here the lesser work to need to transport positive values to minus, and from the duality with the Lipschitz function, it's obvious to see that you have this inequality changing the variable. And so I need some terminology from the homogeneous spaces, because I will work only on homogeneous spaces in the sense of Koopman-Weiss. So as I mentioned in the beginning, which was defined in the 80s of the 20th century, and so the definitions are here. So geometric doubling condition or geometric doubling dimension of omega is the minimal natural D, such that for any ball of radius r, any ball of radius r you can cover by at most d balls of twice lesser radius. And so this minimal d is the not the dimension, but in fact the exponential of the dimension, because we divided by 2, so we need to consider binary logarithm of d to define the dimension. And given a continuous measure, we can consider 2 dimensions of this measure. So the halving condition is here with some h which is positive here, and which implies this inequality for the measure of the balls. And we consider the best possible h star, the supremum of h, with the constant here depends on h and can go to infinity when h goes to h star. And similarly, for the doubling condition, we define the upper dimension of measure in the similar way. So obviously we have this inequality that h is less than geometric dimension of the homogeneous space. So the space is homogeneous if this quantity exists. This is the definition. And h is lesser than g. The obvious examples are some subsets of Euclidean spaces where they all coincide and coincide with the dimension. And so for Hausdorff measure can be defined and so on. It is quite general construction. It does not work. Oops. No. Oh my goodness. How I can return? Okay. This one, it works every third pressing on the button. And so I have 2 theorems to present and to try to explain. So this is the theorem on the best possible representing system. I mean, always in this talk, the representing system with the unconditional convergence. And so the critical constant is, first of all, to simplify the statement, I will consider the case when h is equal to g and to the geometric dimension of omega s. This is the case in Euclidean space. But there are many other spaces and measure where it coincides. And in fact, even it is a condition for h star equal to g star and equal to the geometric dimension. This situation is called Alfor's regular measure metric space. And I will give the statement for this case principally. And so if we consider this joint value of the dimensions of omega and the measure, so we will have the critical constant here, 2 alpha over alpha plus 2. So there exists an orthonormal basis such that this convergence for every epsilon, and this result, this exponent is sharp for any frame, even not only unconditional basis, but even for any frame, this series diverges. And so as the best possible, the best oscillating orthonormal basis is the Haar-like orthonormal basis based on the dyadic decomposition of homogeneous space introduced in 20th century by same Koifman-Weiss and Michael Christ and many others. And so you can use it to prove this property. And so here I give just an example. What happens if there is no Alfor's homogeneity of this coincidence? So it changes, and this exponent is replaced by this one, the geometric divided by the lower measure dimension, and for the sharpness result, so also some relations between the upper and lower dimensions of the measure. But it's not so clever, I can say, as for Alfor's homogeneous. And it is a problem to advance. No.
Maybe you could walk closer to the device. If you go closer to the device, then you can...
Ah, yeah, it's a question of... No, but you don't know this. No, this is... No, it's... да, это обратно. Вперед большая. Ага. Иногда... yes, yeah. And so the theorem 2 is how to behave the general, just generic orthonormal or sequences or frames. And so the generic behave differently, and the critical value is not this 2 alpha over 2, which is strictly less than 2 always. In the previous, the exponent in this. Oh no, it's however. Oops. This 2 alpha over alpha plus 2 it is little. It is a small exponent. It is always strictly than 2, and the dimension can be the big one. How to? No. I cannot find. No, it is not. Okay, the theorem 2, however, I achieved. So the critical value for generic orthonormal sequence or the frame is just the dimension alpha, and the results are here. So if we consider always as always the alpha's regular case with H star equal to G star equal to the geometric dimension, so we will have that for any UK is necessarily alpha plus epsilon summable here, but and it is replaced by 2 in the case if of low dimension, less than 2, and this result is sharp. I mean that we have this divergence for some specific sequence. We can have an orthonormal sequence such that this series diverges, and if the case is regular, alpha's regular, in this kind, if it is not H star and G star, but just H and G, so we can find the orthonormal sequence such that this diverges even for alpha prime equal to alpha. And for the low dimensional case, the results are even better because the critical behavior of the transportation norm of orthonormal basis is just arbitrary square summable sequence here. And so I will comment rapidly this theorem to speak about the techniques. How to? No. Yeah. Ah. You press it? Yeah. So about the proof, so to prove this theorem exactly, I need Sobolev spaces, not only the Kantarovich-Rubinstein, and so this pre-dual space of Lipschitz functions, but also an intermediate Sobolev spaces M1 to M for maximal. Maximal, this is so-called Hiler-Sobolev spaces on homogeneous space, which is defined for M1. This is W1P. W is for Sobolev, and this is the maximal Sobolev spaces, which is defined as a space of functions f on omega, such that there exists a G in LP of mu, which satisfies this inequality. So this divided difference is majorated by the function G here. And the norm is the infimum of all possible G. For the Euclidean situation, this definition coincides with the usual definition with the derivatives, and the space W1P, where the first derivatives are summable with the power P. And so we have obviously this embedding that the Lipschitz is embedded in this space with just a constant here. So in the dual situation. This is the space of analog of the space W1, W minus 1, 2 in the usual notation of Sobolev spaces. This is a large theory developed mostly by this company of Hailish Koskela. This is a very, very nice small books in Memoirs of American Math Society with very interesting title, which correspond to the situation. Op. Yes. And so how the proof goes. So first of all, I prove the approximation lemma. So for estimating the singular numbers, the approximation numbers of the embedding E2. E2 is from Sobolev space to L2. And this is this estimate where G star and H star are measured dimensions. And so it follows the sequence of these approximating numbers is P summable with P larger than G star. If this is the alphas regular case, so G star is equal to H star. And so now to continue and to conclude with the convergence of the Sobolev kind norms of orthonormal basis or the Kantorovich-Rubinstein norms. So I need to suppose that the space M12 has the norm equivalent to a Hilbert norm. And to identify this, I need so-called weak two-Poincaré inequality, which is unfortunately not some property of these homogeneous spaces, but just an axiom. And this inequality is just estimate of the difference, L1 norm of the difference of a function and its mean on the given ball in terms of the LP norm of function f on the larger ball. This is of this kind inequality in the situation of Euclidean space and Lebesgue measure. This is just a simple lemma, but in general it not follow from the other axiomatic, but should be supposed. But for many cases, this is this. No. Oh yeah, oh yeah. Yeah. And then, so I use the Goldberg-Marcus theorem, which work. Why I need the Hilbert space structure? Because of this Goldberg-Marcus theorem, a very old one, which says that in Hilbert space situation, when the norm is Hilbert, the summability property of the norm defined by a linear operator T depends directly on the Schatten class of the given operator. So I have the Schatten class from the estimation of the approximation number, and then I apply this theorem where the statement is different for p less or equal to 2 and p larger than 2, and I obtain the theorem stated before. And so let me show you the last. No, it's impossible. it is a construction of extremal, but this is illustrated. So we have, in general, we have two critical exponents, beta and b, which is here. And for the exponents gamma lesser than beta, all series diverges for arbitrary frame, not only orthonormal basis. In the interval between beta and b, we have for some frames or some orthonormal basis the convergence property, this one, and for some other, which I omitted, the explanation, we have the divergence. So, and for the exponents which is bigger than the dimension alpha, always in the situation of alpha regularity, we have always the convergence. And so this gives some impression of how this is for Schatten classes. Unfortunately, I have no time, and so thank you very much.